And then subtract that one. What's that give us? 1.4? Yeah. All right, so that's the line tangents value. We then want to write it in the correct format in terms of the answer. So f of 1.1 is approximately that 1.4. Good with all that? Okay, then do 3 real quick. Find the exact value. So now use the actual function, plug in 1.1. And then it says after comparing the approximation with the actual value, so the approximation is number 2, the actual value is number 3. Tell me what we can conclude about the concavity. That's kind of that little new idea that we just did in the previous set. All right, so do that. Find f of 1.1. And then see if it's bigger, smaller, and then based upon that, are we concave up or concave down? Oh yeah, we might need a calculator for that one. Okay, get that? All right, so that's our actual value. So now take this, that's the real value, compare it to the approximate value. So if our approximation is less than the real value, that means our tangent line lies where? Above the curve or below it? Below it, which would imply that the curve must be what? Yeah, we have to be concave up. All right, if concave up, we touch the curve one time, but once we get off of that point, the line is always underneath the curve. That's why the approximation would be smaller than the real value. All right, so that's that idea. One more of these, make sure we have this. So this is natural or linearization. Functional value of pi over 3 plus the derivative value at pi over 3, and then x minus the pi over 3. Functional value at pi over 3, cosine of pi over 3 is what? You remember that from back in the day? Good, 1/2. And then we want the derivative value. So that's a negative sign. So that would have to be negative what? Yeah. If the one is 1/2, and this one's going to have to be the root 3 over 2. So we'll do minus root 3 over 2. And then x minus pi over 3. All right. All right, last one. Go ahead and approximate this. And ultimately, you're going to write f of pi over 4 is approximately whatever that spits out. Let's see what time we get out here. What is it? Oh, I was like, man, we're going to be in here a while.
I'm looking at his clock and he hasn't changed it yet. That's true.
That's true.
I
don't ever look at that clock. I always look at that clock. So
138.
138. Yeah. Okay. All right, we're good. We got some time here. All right. Plug in your pi over 4. Where did that go? All right, we get 0.727. Hopefully. And all we're doing is taking this line here, kind of ugly. Certainly have a calculator for this one. And then take your pi over 4, plug that in. Write it the correct way. Yeah.
So what is that line, the Elevex, what is that? Is that
That's it. It is no. It is. All right. So let's say this one here. If I graph the cosine curve, one. Here is pi over 2. So pi over 4 is somewhere here. So this is the actual function. And then when I draw this line tangent in, that's L of x. That's just the equation for the tangent line. So that's L of x. And then the black one is the function cosine of x.
So how can we, why can't we plug in pi over 4? I don't understand.
Say it again.
How does plugging in pi over 4 to the line tangent, wouldn't that give us the value of the line tangent?
Yes, that's why this says approximate. The line is your approximation tool. If I want the real exact value, that's what I've been doing. I'd probably ask you a 6th question, which is then actually, let's find the real value. And then you would just plug that into that. And then that would spit out the real value right away. If it says approximation, that's what the line tangent is doing. It's approximating the value.
Oh, wait, so then the further you get away from the point, the less accurate it's going to be?
100%.
Okay.
Or I'll come to you in about 5 minutes when I ask a question like that. Yeah. All right. So now I think what I was waiting for Joe to ask, and this is kind of a legitimate question, is why would we want to do this approximation method if I actually have the function and I could just plug in a pi over 4, right, Joe? All right. So kind of go here, because a lot of times we just have a bunch of data points, and these data points don't model some nice, perfect little function. So we have to have approximation tools. So this is, as we set this up, table of values is shown in this is shown. It's twice differentiable function. You have x, f of x, f prime, and f double prime. But there's no way to model this with a nice, clean function cosine of x or x cubed, 2x squared, anything like that. All right. So what I want you to do first in number 6, no work whatsoever here. You should be able to write your answer down immediately. Just do the linearization at x equals 2. So if you knew what each part of it meant, the table gives you all of these, and we can throw it down real quick. All right. All right. So the linearization or line tangent, initially we want the functional value. We would have said f of 2. Well, in this case, f of 2 was that 5 right here. We're just using all these values, not all of them, but getting the values from there. And then we do plus, and then we want our derivative value at that point, which is a negative 2. And then x minus a 2. Okay, or you can just do minus 2, x minus 2. All right, I'm actually going to do that because I just don't like the look of that. All right, and then that's it. Now do 7 and 8. So now 7, just like we did on the front page, I want you to use this line to approximate f of 2.2. Because now is 2.2 one of the values in the table that we're going to be able to find the exact value of? No. So we're kind of stuck in terms of we don't know what f of 2.2 is. There's no way to find it. But we can approximate it if we can get a tangent line close enough to it, which we can. Once you have that, answer number 8. Is the approximation that you just found in number 7 going to be greater than or less than the actual value? And we just said there's no way to find the actual value. All right, so find 7 and then answer 8. All right, 7. Oops, I don't want that. Okay, do we all get 4.6? Good. Write it the correct way. Use the approximation symbol. Use f of 2.2. And then now this, we know what the approximation is. That's 4.6. We don't know the actual value, but we should be able to state if the approximation is greater than or less than. So what do we think? Is this guy greater than or less than the actual value? Sean?
Would be less than his concave up.
Good. It has to be less than. And then we would say because, I'm going to say f of x. We don't want to use it too often. But then he said because, and we also have a line tangent. So we wanted to say the function, and then he said a perfect is concave up. Don't necessarily need to write this, but just so we're clear, if we look at it further, plus the people I'm recording it for didn't hear this part. Therefore, that line tangent, squeeze that in there. Pretend that says tangent lies under the curve. All right. Yeah.
So we don't have to explain like why we know it's concave up. We just write that it's concave up.
Yeah. Yeah, that's a good question. We probably do want to say that the second derivative is a positive 4. No, actually we don't. What we want to justify is y is greater than or less than. And the reason that is it's concave up. We're not justifying y is concave up. We're adjusting y is greater than or less than. So that justification is stating that we are concave up. And that's because of the positive 4 there. You want to be heard to say that. But what we're stating is that we're less than, and that's because it's concave up. Okay. Yeah, good question though. All right, so now Joe's question here. It says, would the line found in number 6, so this line here, where we're tangent at the x value of 2, be a good approximation tool for the value of f of negative 2? So we just used that line to approximate f of 2.2, but would it be a good approximation tool for f of negative 2? What do you think, Joe? No. And pretty much what Joe said a little bit ago. As soon as you get too far away, and that's a relative term, so there is no necessarily exactly what's too far away. But certainly if we're going from a positive 2 all the way to a negative 2, that probably is too far away. All right, so we would say no. The value of x equals 2. Negative 2 is something along the lines, I'm going to say too far away. Move this up a little bit from the point of tangency. All right. All right, so that's that stuff. Last thing, how linearizations lead to what we call differentials. So what I did in this first setup here, this here, if I told you to write the linearization for this curve at x equals 3, this is what you're going to get. This is the functional value at 3. If I squared it, if I took the derivative 2x and multiplied by 3, I'm going to get 6. So I'm giving you that part of it. All right. What I want you to do, the first sentence, is using that linearization, find the y value when x equals the following values. So go to x equals 3, take that line tangent, the linearization that we gave you. Actually, I'm going to do this in red. Oops. And then all I want you to do is take the x value of 3 and plug that in. All right, notice how you're going to get 9. If I take 3 and plug it into the original function, what are we going to get? 9, because that's where we're tangent to the curve. So these next 3 are really based off the idea that when I'm at x equals 3, that's where they share their point, the 0.39. Okay. Now go to number 2 and then be overly thorough here. So what I'm going to do, take the 9, don't skip any of these steps, and then 9 plus 6. Go ahead and let the x be a 3.1. So we just rewrite it with the x value of 3.1. And then again, don't skip this. 3.1 minus 3 is a 0.1. And then we get 9 plus 0.6. And then finally, that y value is 9.6. So this is saying if we stay on the line and we go from 3 to 3.1, that our y value on the line would increase by 0.6. So the second thing I want you to state now is state the difference between that y value here and the y value at the point of tangency. So it would have been a 9. Notice how I went to 9.6. So we're going to write it like this. dy, the difference in my y, is 0.6 units. So we would have increased our y position by 0.6 if we stayed on the tangent line. Okay? Next one. Same exact thing. Bless you, Mary. Go ahead, plug in 2.85 minus that 3. And again, we'll be overly thorough here. Show that that difference is a negative 0.15. And then negative 0.9. We multiply those together. Our new y value then is 8.1. So this now, if I was at 3, I move left a little bit to 2.85. Now my y value, what did my y value do? Yeah, decrease. So we're going to say the dy is a negative, and then it went from 9, where we started, to 8.1. So we decrease by 0.9. All right. And then last one. And then we'll talk about why we're doing this. Just want you to kind of see something here. Go ahead and let 3.25 be the x. Subtract those. Multiply them. And then combine those two values. So our initial y value plus that should give us 10.5. So again, here's the initial y value at our point of tangency. We went to 10.5, so we grew by 1.5. Okay. So what I now want you to kind of look at, and we have 3 examples, 2, 3, and 4 that will show this. If I now go off to the right and I ask you, how did we get dy in all of those? What was common about all of those? Like, where was that dy? So here it was 0.6, negative 0.9, 1.5. Where were those values gotten from? What were we doing to get those? Okay. So every one of them, what were we multiplying by 6 though? Oh, I'm so close. That's good. You almost said it perfectly. So we took the 6. What did the 6 represent in all the linearizations that we did? The slope / the derivative, right? And then he said the word difference, and I thought he was going to say it perfectly. It's still pretty good. Didn't we get subtract here, subtract here, subtract here? Aren't we subtracting x's right there? So what we are finding is we're taking that derivative. Oops, make sure you put the tick mark there. And we're multiplying that by the difference in those x values, the original x value and whatever x value that I gave you. All right. So notice what we've just set up here. If we did a little bit of algebra. Now, this is differential notation, so maybe box that thing up. If I ever tell you to write something in differential notation, this is differential notation. But isn't that really just the same? You don't have to write this necessarily, as dy dx is the same as f prime of x. If we just did the algebra and divide that over. All right? Because what I'm going to have you now do, and this is all we're going to do, is super easy. I want you to write these derivatives. So let's first take the derivative. So dy dx equals 3x squared minus a3. I want you to write those in differential notation. So all that really means is I need to solve this for dy. So multiply the dx over. And then when we do that, this is differential notation. And right now, that is all we're doing with these. All right. We'll do a number of things with them later in the year, but right now, that is it. There's a whole class called differential equations, all right, at some point that a lot of you might take. All right. So that's our differential equation. So with this one, same thing. Take dy dx, and you get 4x plus sine of x. That's our derivative. If we write that in differential notation, you're just multiplying that dx over. Like so. And then eventually, as in right now, because this is not hard stuff and you probably could already do it, we don't even bother with the dy dx. We just do dy equals, and then right away, we just take our derivative and have the dx over there right in step number 1, and then you're done. All right. So this is differential notation. It's a differential equation. Yeah.
Could you explain the first part, the differential notation? How did we get that?
We got it from all of these up here. So notice how this 0.6 was gotten from this product, and the negative 0.9 was gotten from this product. 1.5 was gotten from this product. So our dy every single time, so that's what I started with right here. Every single time we got it by taking the derivative value of 6, the derivative value of 6, the derivative value of 6. So that's why we then have the derivative value. And then we multiplied that by, see how we got this 0.1 right here? The 0.1 was us subtracting our x values, the original x value and the new one. The negative 0.15, the original x value and our new one, we subtracted them. So every single time we took our derivative and multiplied it by the difference in our x's. All right, so this equation right here is what's called differential notation, okay? All right, that is it. What time did I say, 38? Oh, you got all kinds of time to burn there.